Hi everyone, welcome back to our DDLC seminar. This time we invited Professor Lee from the University of Howard and to be our today's speaker. So let me have an introduction for Professor Lee and then we can start our talk today. So Professor Lee is a professor in electrical engineering and applied mathematics at Harvard University. She received her bachelor degree in mathematics from Zhejiang University and also PhD degree in control and dynamic systems from Caltech. She was a postdoc associate at the MIT from 2013 to 2014. She has held a variety of short-term visiting appointments, including the Simons Institute for the Theory for Computing, MIT, Google Brain, and MERL. Her research lies in the control, learning, and optimization of network systems, including theory development, algorithm design, and applications to real-world cyber-physical society system. She is an IEEE member and a senior editor of IEEE Transaction on Control for Network Systems. She was an associate editor for IEEE Transaction on Automatic Control Systems Control Letters, IEEE Control Systems Letters, and also served on the organizing committee for field conferences and workshops such as IEEE CDC, AMCE Energy, and NSF workshop on reinforcement learning. She received the NSF Career Award, AFSOR Young Investigator Award, ONR Young Investigator Award, Donald P. Ekman Award, McDonald Mentoring Award, IEEE CSS Distinguished Lecturer, and also IFAC Distinguished Lecturer, IFAC Murphy Tom Medal, and also Robert T. Young Researcher Prize, along with all other awards. So let's give Professor Lee a really warm welcome and give the time to Professor for today's talk.
Thank you, Shantian, for the introduction, and thank you for organizing the seminar series. It's a great pleasure to talk about the work I've been working on the past few years, especially with my collaborator from Google, Bo, and on the representation-based conjunct learning. I somehow also put in the title about from the data to action for intelligent physical system. So I will just do a very quick motivation of the slides, of the talk. So I will just do this. Excuse me. Some part of the computer. Good, great. So let me get started. I will just do a very quick introduction. So I've been seeing so many exciting news of the deep reinforcement learning, like from the AlphaGo and to the large language model, and recently for the VLA. So all those reinforcement learning, like why people, and also beyond those applications in those computer systems, people also using the reinforcement learning on some other tasks like the biology system. So one of the common thing in the deep reinforcement learning is kind of very similar to the control feedback loop. So we have an environment, we have an AI agent. The agent will observe what's going on with the environment, which is, we can call that state. And based on the state, so the agent will decide what action. So it's kind of the control policy we want to find out. So how are we going to decide what really the control policy going to do is we go ahead to base on the reward of the system, or you can say based on the cost of the environment. So our action goal is to find feedback control policy to optimize the overall accumulated reward. So one advantage, like why so many different community were using the reinforcement learning tools is, as I put in here, is that we typically assuming this black box of the environment is so hard to model the system. So we assume it's unknown and we just go ahead to play different policy, improve the policy, and again, eventually to find a better policy. So we see so many exciting news. And like a big motivation for the talk and also for many people's work, especially right now, people working on embodied AI, is try to transfer success of the AI from the computer system to the real world physical system. So here I put in some examples of the system I've been working in the past. So one's a power system and the transportation system, the robotics, and the last one is about the biosystem I've been working on. And I will kind of touch base those applications slightly later in the talk. So when we dive into this application, let me talk about some challenges. There are many challenges, and I will only touch those a few challenges, and I will kind of brought those applications to illustrate what the challenges we were referring to. Now, first, always when people say believe the scaling law of the large models, that you have large model, you have large data, you want to learn the things you want. But when we try to focus on the physical system, the first challenge is about the limited data. So even though we have this kind of Internet of Things, like a huge amount of data generated by the IoT devices, but now once we look at the application, let's talk about the, for example, power system. So for power system, like one thing we really want the new computation AI method or data method is to help in guiding us to do the better smart decision making when there is extreme weather scenario, like the winter storm, the heat wave. Like we do not really have, even for that, as a human expert, we do not really have this kind of data to guide us how we're going to do it. Now for the transportation, like different city have the congestion. So can we actually use the AI to reduce the congestion of the traffic system? It's kind of very different from like using the expert data to the imitation learning. We actually have very limited data about how we're going to really address those scenarios. And now when people say, oh, for some system robotics, we will have a simulation, and I will talk about sim to real gap. Like it's still like there's a far away from the real simulation to the real system. And now there's a lot of startup companies trying to just go ahead and do the data labeling for the robotics data. And for the biology, even worse, because one experiment will probably take in like 2 months to get just one data point. So it's very expensive and a very sparse data point. So that's the first challenge. And second challenge, as I mentioned, right, the people say we have some simulation for power system and for the robotics. And no matter how good the simulator is, there's always a gap. And always like how we can actually using the simulator and we will get in some real data, go back to improving the simulator. It's still like how we're going to making the interaction loop be more efficient is still open question. And moreover, when we really talk about the physical system, the safety is always the most critical criterion for us to decide should we actually implement the algorithm or not. Like if we here putting the blackout as an example, like we try the best to avoid the large scale blackout. And for the robotics, is try to avoid the robotics either going to hit people or the robots going to fail. And for the transportation, the safety is always the most critical criterion. So now those are the standard challenges when we even talking about the single physical system. Now, once we dive into like the physical system, when we really interact with the world, as I mentioned, especially for the power system and the transportation, so we care about scalability. So like what do I mean by the scalability? So we will have those individual device, like the sensing device, actuated devices going to be deployed in the system. And we would like each device can make the fast decisions once they see something's changed. So this is different compared with like individual prompt that you go to call the GPT and then you're going to send in the command to the data center. So we would like the individual physical device to make action fast, because by the time once you receive like basic on the communication, like in the data center to decide the decision probably change, and they're going to be hitting the like back to the safety. It's going to probably hitting certain kind of obstacles. It's going to damage the system. And now when we talk about scalability, like one thing for individual device, no matter what, like because limited by the size. So we have a limited sensing, communication, and computation capability. And how can we actually use the small models to making the fast decisions and reliable decisions? So that's another dimension of the challenge. And the last one, I think that's a kind of pop up in all those applications for reinforcement learning. The reward is always the key to success. Now, when we dive into the physical system, the reward is actually not really that clearly defined. So as engineering system, like say power system, transportation system, or robotics, we can always list like a sequence of metrics we want to achieve. How are we going to translate this kind of metrics to a reward function and guiding the IO policy to trend, which is still like people try different kind of engineering solution. And when we train one engineering system, probably it's not going to generate to other engineering system well. And this is like about even the single agent. Now, when we're talking about emission scalability, so we have individual devices, individual agent, individual players. So now individual players might have those conflict interests, is not going to be perfectly aligned. So what should be exactly the reward? Like individual reward or the like total reward to get the entire system to achieve a global desired behavior. And this is still a lot of like ongoing work. And for the power, like I also want to talk about the biosystem. Like that one even like it's harder, right? I roughly know what I want to achieve for this kind of biosystem. How are we going to translate this kind of biophenomena to some quantitative phenomena that I can use in the IO mathematical computation tool to design the experiment is again as like open question. Like putting everything in the summary, as like for different application, they might draw core different method. So what's really the kind of common scheme that we can use? So in my research lab, we had a lot of collaborators from like different area, like the power system, the biology, the building, the energy system. So when we work together, we always first trying to discuss, so overall, what's really the goal? Even I put in the FG here, looks like it's already quantified. So we'll try to making sure what kind of the clear quantified metric I can really put. What's kind of some metric I haven't really like able to quantify it using the mathematical way and figure out a way to bring the mathematical way to model it. So if I dive into it, so typically, once we talking about dynamical system, as I mentioned, for the like environment, we'll have a state and we will have an action. So once we have a set action, we try to model how the state evolved. And as I mentioned, the system has a huge complexity and uncertainty. So we're putting some kind of uncertain variable here to remind, okay, this like the system probably even will have a model, but it's not really a full model. So what uncertainty come up? So we have a G as a cost function, we have the F as a reward function, and there's some other constraint. And now when we're talking about the like scalability, so we're trying to put in the control policy on top of the data sample. So we like, what's really the communication, the information? So we put in this as the admissible policy, like what's really the information infrastructure. That's kind of including the sensing, including the communication. So once we put in those, this is kind of the mathematical way to describing the problem. And you can imagine like every problem will call different tools. It's not like a magic tool will work for all the system. So mostly we'll kind of combine the mathematical tools, the system structure, and the knowledge to find a solution. So those are the applications that my group have been working in the past. So we, as I mentioned, we had the energy system for power system, for the house zero. And my own group also has the robotics, like trying to close the loop within the group. And we also work with the biologists on different kind of bio experiment. So for different applications, they actually had a different kind of data set and different structure, and it's different, like I would say sometimes it's like the different domain knowledge can play a different role in design algorithm. So this is a quick motivation of the talk, and this kind of give a overarching picture of like what my group have been working on. But today I will just focusing on mostly on the mathematical algorithm part. So how we can actually using some algorithmic tool to developing some like the baseline, the general method that can probably apply to a broad class of dynamical system. So I will focus on the representation and I will touch the system structure a little bit. So when I talk about representations, I will just first let's dive into the model problem formulation. So if you look at this problem formulation, it's very standard, like control textbook dynamical system problem. So we'll have a state, and we have a control action, and we have system dynamics. So this is what like kind of state space model. As I mentioned, they always have some like uncertainty from the system and also have the noise in the system. And we have a reward, it can come from the negative cost. So the goal as a discounting factor is to find feedback policy, try to maximize the over like accumulative reward. And putting the discounting factor to just kind of making sure the reward is kind of well defined. Now, so as I mentioned, this is actually very standard stochastic nonlinear control problem formulation. So we do have a lot of tools, and this is kind of like I would say incomplete list of different kind of tools. So if you like took a nonlinear control class and probably already kind of cover most of those methods. So I want to mention like for those methods, I'm not going to dive one by one. So for example, feedback linearization is a work for special class of systems and not like working for general system. And then for like the SOS tools, it's a very nice computation tool, but the computation is very expensive. Even for like when I was a student, I took the class, even for system with like 3 or 4 state and try to find using SOS to find some control policy, becoming very computationally difficult. Now, With all those methods, when I started working with, like I did my sabbatical in 2021 at Google to 2020. So my team was collaborated was mostly from the computer science reinforcement learning. So I was kind of asking the question, can we actually making it the reinforcement learning method like kind of applicable to the nonlinear control just as a computational method? So what do I mean by a computational method? Like even you assuming you know all the information, like we know F, we know R, we know everything. And I just looking for some computation tool to get some controller. And I want to then like first don't worry about too much of the control performance. I can just use that computation tool to get the controller, and then I'm going to evaluate the control performance. So that's how the collaboration gets started. And then we look into the problem, like see what's the difficulty of it. And later I will like dive into like what's really the IO method and how we're going to implement and what's really the challenge like I faced when I initially working on this problem. So for the talk, I will like the motivation, I will have a two-part. First, I will just focus on the single plant, and I will also just focus on the model base. You know, everything, just kind of looking at the IO as a computation method for the nonlinear stochastic control, and to figure out how we're able to reuse the IO as a computation tool. And then since I developing the control method, using the IO method is actually very straightforward to extend to the data-driven unknown model. And I will talk about how we're going to use this method representation to work on the system without the model knowledge. And in the last probably 10 minutes, I will just talk about how to scale up the method. Now, in order to kind of talk about how we're going to use the IO method as a computation tool, so let's do a very quick review, like more mathematical review of the reinforcement learning. So in the reinforcement learning, if you look at this problem, it looks similar to the nonlinear stochastic control problem I introduced. We have a state, we have control action, and we have a reward, we have discounting factor, and the goal to try to find feedback policy. So here the feedback policy like is actually a stochastic policy based on the current state, try to decide an action, and the action we're taking from the probability distribution over the action set. There's only one small difference, which is the state transition. So previously I was doing the state transition, like state space model. And now I'm actually doing the state transition probability model. And I will talk about more like what's the benefit, but just looking at the state transition probability later. Now, what is the IO method? There are many different types of IO method, and typically I just kind of usually want to clarify, like classify them as the actor and the critic. So in the actor, so because we do not really know what really the optimal policy should be, so natural way is just go ahead to parameterize it by some neural net. So once we parameterize by a neural net, now the next step is do the policy optimization. By policy optimization means to evaluate the policy gradient under this policy structure. So how people like to evaluate the policy gradient, I can imagine this is kind of closed loop performance. Even it's hard to evaluate the cost to go, it's even harder to evaluate the policy gradient. And like I'm not going to dive into the math equation for the policy gradient theorem, but like the policy gradient theorem is building the connection from to just evaluate the policy, which is the cost to go, to evaluate the gradient as a sample-based method. And then what's really the cost to go? The cost to go, they just evaluate the expected reward under this policy given an initial state action period. So now how people, again, back to the policy evaluation. So if I have a very large state, large action, like say continuous state, continuous action, it's hard to know what really the formula of the Q function is. And then what people can do is go ahead, grab another neural net representation for this Q function. And then to using certain kind of learning method to updating the additional like the neural net parameter omega. So the reinforcement learning method will have a different kind of like interaction between the actor and the critic, and you can probably just like do pure critic way, or you do like it one loop of actor and the critic of each round. Now, so as I mentioned, like these are two parts. When I first started, like trying to grab this IO method, there's always one big question about what should be the parameterization. So there's a different kind of neural net. Like for the large models, people always do the transformer, and there's also like the UNet, all those things. But then what should be the representation for those two neural net? So majority of my talk, we're just focusing on talking about the Q parameterization, like how are we going to evaluate the Q function? So many theoretical work will kind of assuming, oh, there's a function approximation class. And under that function approximation class, I can evaluate any kind of Q with absolute accuracy. But like, what kind of function class can really guarantee that? Like, it's very hard. It's not really like jumping from nowhere. So that kind of question, like we started is what should be the representation? Like if I have my nonlinear system, like that's why I start with my model-based method. So what's the function approximation class that I can actually guarantee? Like no matter what kind of the dynamics, no matter what kind of R, and I can making sure the QW can approximate any kind of true Q. So that's kind of central question. That's what I mean by the representation. If you actually try those IO methods, you will like, when I started, it's very hard to really making the IO method work because if I stuck with kind of like bad Q parameterization, it's either over parameterized, on the parameterized, it's very hard to making the method kind of keep learning, has a very nice corners curve. So then we start that question, what should be the Q representation? So now we dive into the how people actually model, like how we actually using the data to evaluate the Q. So almost everything will kind of coming back to the Bellman equation, Bellman recursion. So this is the Bellman recursion to evaluate the Q function if under a policy pi. As well, it's going like given the current state and taking the action A is the cost to go will be equal to current RSA plus the expected future reward. So that's what the formula is, right, from the state transition probability. Now, what's going to happen? Let's put in this as kind of assumption, this typical theoretical RL and the theoretical control will start with some assumption. So if I assume the state transition probability has this decomposition. So this decomposition, like I put in here, I split in the two color. So one is the PSA, the current state action, and the future S prime. If I have that, what's going to happen? So I will substitute into the Bellman recursion. So that has integration, has a P state transition. So the integral has a linear property. I can actually get the inner product of PSA out. So once I move that part out, what it says is a Q function is actually state in this feature space. So the Q function will stay in the feature space of PSA, which is come from the state transition dynamics and plus the RSA. As I assuming we know the R, we know, and typically even the model free method, people also kind of specify the R, the reward is kind of we specify it. So this is actually great news. It means now I actually really have a natural function approximation to approximate the Q. And this is like indeed, when I started doing this work, there's many nice theoretical work to study if we have this kind of state dynamics sitting in that lower dimension of the feature space VSA and the mu S prime. So what's really the sample efficient? And you can also imagine like now, not just like look at the Bellman equation. So that's one of the sample efficient. Computationally, it also can be efficient because now when I try to update my Q, I just need to update the W, which is just this square power. So that's a great advantage. But now natural question is here. So let's start with this assumption. But does this assumption valid? Is this assumption valid for any kind of system? What is the example? Now we have that question. So then like we look into back to the nonlinear state space model we have earlier. Now I'm putting this kind of as example. So now this is the state space model I brought up earlier. We have FSA, we have the, like say epsilon is a Gaussian noise. So we can write down this Gaussian noise, like the state space model as a state transition probability model. And that state transition probability is a Gaussian probability. And the Gaussian probability is a positive kernel. Once a positive kernel, it will the FSA and S prime. Not sure whether you can see the mouse here. So FSA and S prime, so kind of X and Y. So that's what I mean by positive kernel. So similarly to the positive definite matrix, we can do decomposition. So we can do decomposition on this positive kernel, and decomposition is actually what naturally tell us what should be the feature. So now this is apply one decomposition theorem. There's actually many other decomposition theorem you can apply. So when we apply the Bohan theorem, so we got the two feature and the inner product, like we defined, like it's kind of not defined earlier. It's kind of defined by this theorem, like it's kind of inner product coming from the expected rho omega, which kind of standard norm distribution, and the feature space is going to be our familiar, like the Fourier series. And the FSA here, you can look at here, is kind of embedded into the feature. So if I have the model of the system, I can embed like what should be the feature I should pick. I just go ahead using this kernels. I'm putting my FSA inside the kernel, and that's going to be my feature. So if I summarize, it's this. So it's kind of like, this is not assumption. If I start with a nonlinear stochastic state space model, and like for this one is a Gaussian noise, I always have a linear feature decomposition. And you may ask a question, like, what about other, like, this is just a Gaussian feature. So as long as the noise model, I can write it down as the positive kernel, I always have the decomposition. As the later part, I will also dive into more. Like, this is not just about like given one noise model has a decomposition. So like I just hold that question for the second part. I will talk about more like beyond like where this kind of decomposition from, what really the spectral decomposition means for general probability distribution later. But now for now, you can like just kind of summary is any kind of nonlinear stochastic state space model I can represent in this decomposition way. I naturally got the feature and the model structure, the F, naturally like fitting into my feature is like, it's not like I throw away my knowledge of the F. I can just keep my F in my feature space. With that, now back to the algorithm. Like we actually don't need to change much algorithm. It's like given any kind of nonlinear stochastic model, I'm putting the F into that Fourier series, and that's my like VSA and mu s prime. So, and the algorithm is like here, I just need to use that VSA to update my Q to learn the W. And you can still stick to any kind of your favorite IO method, either it's SAC or it's PBO. You just go ahead to grab the method. Like just you do not need to change much. You just need to kind of change the parameterization of your critic parameterization. So this is the performance of our algorithm. So we first really just focus on the model-based method and on those standard nonlinear control problems. That's our control community usually will test. So pendulum, double pendulum, and 2D dimension drum. And you can look at here, compare with some others nonlinear control method like iterative LQR and Koopman. And this also, I want to also highlight the energy-based method. So energy-based method is a global method. People try to find kind of the optimal, the kind of good energy-based function to guide the control design. So like compare all those methods, like you can see our method achieve the best performance. And especially if the system has noise, our system will do better because all those other methods kind of like, for example, iterative LQR, you have to kind of do iterative linearization. So if you have a real stochastic, right, whatever you linearize earlier is actually not really exactly what's going on with the real system. But our method actually naturally harness the stochastic of the system. So you can say when has a noise, so always like our method can do the best among compared with other method. And like additional thing, the advantage is rather than just like say deep IO grab it as a computational method. Now we actually can go ahead to analyze the performance. So we can provide the performance guarantee of our representation-based IO method. Because now look at our representation. So we had the first is the feature truncation. So we have the linear decomposition, and that's the inner product defined in the Hilbert space in order to make the method be computationally. So we have to do the feature truncation. And so that one map arrow will come from the feature truncation. I have to use the finite feature, but I have a way to gradually adding more and more feature to making the say dynamic transition, like the approximation better and better. And the next arrow is the statistical arrow, which is on the Q evaluation. I've again needed using the sample to updating the W, updating my Q function. And last one is the policy iteration. And we're going to do the policy gradient again and again. So like the paper has the end-to-end sample complexity guarantee under list of max parameterization. And so if you're interested, welcome to check the details. And we also open the code. So I think for the code, we tried hard, like you can just put in your dynamical system into the like our toolbox. and then you can just go ahead to run the algorithm and to get in the method, to get in the controller, and then to see how good the controller performance is. Now, this is about the model base. I was like, now let's dive into the interesting part. What if we do not know the model? And then what's really the meaning for the decomposition? So when we don't have the model, one straightforward way to do it is to like system identification, and then to go ahead, do the feature decomposition and design the policy. But another interesting thing is this. So since the method the IO method, what I need is a feature space. So I do not really need a state space model. So if I do the feature space, so I can go ahead using the data to learn the state transition probability with this decomposition structure. Now we put in that, so we can go ahead to learn this decomposition from the data. So there's a kind of straightforward way. Okay, if that is this equation arrow, like the first spectral density estimation, it's just kind of to minimize the equation arrow. And the second one is like, since I said this has a connection to the decomposition, so kind of similar to those eigenvalue decomposition, like do the singular value decomposition on the function space. So those are more like, just view this as the function, like kind of standard function. But another interesting thing is this. So what we learned is a state transition probability. What it means is a probability distribution. So what probability distribution? Now think about what really generative AI have been doing. Generative AI is trying to understand data or generate data from an unknown distribution, and this is a distribution. So now once we like realize what we learned is a conditional probability distribution, we can go ahead to grab the statistical tool to learn it, rather than just treating it as an equation, like putting like that's kind of the first two method. So this is the first method. You can just go ahead to do the MLE. So MLE has some fundamental computation method because of normalization. So that's why like in the recent years, so a lot of like new generative AI methods have been developed. So for example, we can do the contrastive learning. By contrastive learning, you're going to generate like contrastive noise, like which is not from your true dynamics, and then using this kind of like the true data and the contrastive data, and then to learn the P S prime and S given the SA. And furthermore, we can also even go ahead to the score matching method. And moreover, we can also apply the diffusion models to learn the probability distribution. So like here, I had a, like you look at the reference, like all those references are not like some of like our paper, but mostly they actually from the generative AI field, like which just tell people how to learn an unknown distribution from data in a sample efficient way, what the guarantee they will have. So if you're interested, I do highly recommend like diving into those papers. And like those papers, based on my background, I found it kind of speaking to me. I can like go ahead and send all the background. So if you're interested, I do highly recommend the paper I put in on the slides. Now, so this is kind of, in my opinion, it's kind of exciting part is like now we just kind of really building the connection from the kind of nonlinear control with the generative AI, and kind of in a very natural way. Now, again, but still for the IL, the fundamental difficulty about exploitation. So far what we have been doing is kind of on the high level, like follow the principles that people have been doing. For the system identification, so the way you can encourage exploration, you can kind of draw the F from a class of function class, and you will like always updating the probability distribution of the function class, and that's where you can add randomness, encourage exploration. And then another way to do it is like similar to the UCB bonus function, because I know my model is not accurate, so I can carefully design the bonus function, like BSA here, to encourage exploration. So like empirically, like later you will see, like we have a very good empirical performance. And I do want to say, like theoretically, I do think there's still a lot of room to go ahead to dive into more. Like if I really want to minimize the sample complexity, what's really the better way to really control the exploitation trade-off. And it's also on the different kind of like the distribution space, you will have a different kind of way to balance those exploration and exploitation. Now this is just a table to showing our representation IL is doing better than other method, but I don't want to spend time here. What I want to dive into is like the use of the representation is not just, oh, now do the magical task. So the representation will provide a principled way for us to really go ahead to work on the like design the control policy for real physical system. And this is the one example. I'm going to talk about the sim to real gap and to see how this representation can be used like to maximize the use of the past data and to give us a principled way to add, like think about how to add a new feature and how to like using the new data in an efficient way. So now let me talk about what the sim-to-real gap I'm going to mention. So I'm going to focus on the sim-to-real gap in terms of the transition probability, right? Which is usually the case. Like I will simulate, I will model how the state transition will look like. And the real physical system, like because it's something we did a model and also the environment is different from the lab. So there's a gap. So that the P node and the P, they are different. So when they're different, the natural thing because I was focusing on the decomposition, like the feature space come from the state transition probability. But the state transition probability, they are different. So what this means is like when I using the simulator, I learn the feature, and I learn when I using the simulator doing the RL, I learn my Q function. So they're sitting in, like let's say the final node, this space. And this final space is not able to recover the real P, there's a gap. But the good thing is I stay in this kind of spectral decomposition, kind of like if I view the like fixing the feature phi SA, it's kind of linear with respect to this nonlinear feature space. So then think about what we did for the vector space, right? We have a certain kind of basis we pick. And now we know given the original basis is not able to cover my new information. So how are you going to add a new basis? I can just systematically try to add new bases in an efficient way in terms of, like putting here, from the function space viewpoint. This is my true Q function I would like to have. This is my original phi. I fit in this function space, and I need to decide some new feature and to making sure that like adding the old feature, new feature will cover what I need. So if I want to do the data efficient way, it's better to just making the new feature, not going to sitting like have less overlap with old feature. So what that one means is that orthogonal requirement. So the orthogonal, like here, the orthogonal requirement is on the Hilbert space that I defined earlier. But since now we are talking about the scenario that we do not really know the model, so we cannot really exactly evaluate the Hilbert space. So the way we're going to do it, we're going to just using the data to approximate, to judge whether the new feature we add has more information, have like at least overlap with the past feature. So now you see that's another advantage once we really put into this representation and then we know how to really systematically control the information overlap between those features. With this kind of framework, and we actually using like developing like the sim to real framework for those kind of robotics implementation. First, we'll have a physical simulator. From the simulator, we'll learn the feature. And using the feature, we'll do the RL, we'll learn the policy, and then we'll deploy the policy. So as you will later, you will see the simulation, like the initial policy usually not going to work, it fail. But even if it fail, it's collecting new data. So once it collecting new data, like in the classical way, then people just, okay, now I get the new data, I'm using the new data and then to put into the buffer to update my control policy. Here, I use the new data. I'm also going to use the data to update my feature, adding more feature. So with a new feature, again, that I will train the RL, I will update my control policy. So like now I'm going to use the data two-way, updating my simulator, which I mean by the feature, and also going to update my control policy. Now let's look at here the comparison. So you can see like this is a simulator policy. Like after few seconds, it just crash. And this skill transfer is just using the new data to kind of run the IO further. It's doing better, but because the data is kind of still limited, and again, it's like crash. So the last one is the one I was mentioning, that's our method. Once we get in new data, we also going to we also update the feature, which kind of like we also update the dynamics. Since we have updated dynamics, we're able to do better given the same amount of data compared with the other skill transfer. So this is some trajectory to show how the result look like. And then we had a for the paper review, and then people were like, hey, now can you further change the environment and to see how the representation method can be adaptively updated according to the environment. But once you have the change in the environment, you will get new data. And you can see that this is once you put in the wind, right, you can look at the initial overshoot. It's not able to really achieve the goal nicely. So this is kind of original policy. But we got new data. So we're actually putting this new data into our representation learning and also updating the policy. Just after 3 rounds, it's able to stabilizing the port order nicely. And then we also evaluate. Now, because you look at our feature sheet, we didn't throw our feature. Another nice thing is that even if your original feature is not useful, you can just go ahead, like naturally the weight function, we're just putting a lower weight. But then our feature space is naturally just going to kind of expand and will cover all different kind of environment. So that's what's being demonstrated from the sim to real transfer. And now I also do a quick introduction. So I had a feature of talking about the PSA, and there's also another feature mu(s prime). So the advantage by really using the data to understand state dynamics in this representation viewpoint is we can actually using the data from all different sources. So this is one illustration. For imitation learning means you're going to have an expert to run the system, and then you mimic the expert. So it's compared with just training RL from scratch. It will be faster, safer, because initially they got an expert to run the system better. But the disadvantage or the difficulty for those expert learning, imitation learning, is they usually have very lax expert data, right? And when we have a design one robot, right, that's what's going on. People are trying to do the data labeling, asking human to do the tally operation to get in the data. But no matter what, it's overhead limited data. So what we able to do is for the representation for the state transition, since we just need to understand the transition better, so we actually can use the non-expert data, using this kind of data to understand state transition, and that's what also helping us to learn the good policy. So like this paper also published in the IROS. If you're interested, you can take a look. Now, as a advertisement, so like last month, we finally summarizing all the sequence of work. So all the work actually took us 4 years or 5 years. So we had a sequence of all the work, like especially diving into a different kind of generative AI method to learn this representation. So we finally wrap up like summary, a survey paper. We put in all those methods together and discuss the pros and the cons. We also streamed our code. Like now, if you really want to try, grab the code. So this is the GitHub I recommend. So we clean all the code, and also for this survey paper, we take this as an opportunity to also run the vision input. So for this one, we also have some like using the vision input as the state and doing the control policy. So like I highly recommend. I would like to hear the feedback. So we tried hard to clean everything. Now, I think I don't have much time, so I will just do a quick introduction of how this representation actually can also scale up to the large-scale system. So for the large-scale system, I'm just like give a kind of like a big picture, like what's really the network system I was referring to. So we have a network. Each node have a state. Each node have an action. So the dynamics is like one node state will depending on the neighboring state and his own action. The stage at every node can also observing something like locally cost or local reward. So again, like ultimately, we like have a control policy matching from the entire state to the action. Have a control objective, like try to maximize the long-term discounting reward. So when I look at the dynamics, I focus on the local coupling one, like this can give me some system structure to allow me to figure out some scalable control policy. So this is coming from like those local interaction come from the system, the application I've been working on. Like for the energy system, like say the temperature of a room will depending mostly on the temperature of adjacent rooms, and the congestion for road will depending on the nearby roads. That's where the local interaction come from. Now, when we look at that network control problem, like the first challenge about information constraint, because first, even people has a way to learn the global control policy, will be hard to implement in reality because like some data center will need to aggregate all the information, and there's all the sort of like sensing, communication, all the issue pop up. So we need to do those kind of like local controller. So by local controller means just individual node just based on some local observation, like from himself and some like neighborhood, taking the local action. So this is a problem that's the network control people have been working for many decades. And this is like still, like if you put in this kind of fundamental question, like how much optimality do we sacrifice? Like this is not about how to find the controller. It's just like if we being forced to do the local controller, and how much optimality does we really sacrifice, and how that the performance degrade with the degree of the locality. Why this question is important, right? If my local control policy, no matter what, is going to be bad, it's actually really sad news on the one hand, and then like probably then it means I need to really improve the information infrastructure, right, to add a little bit more information to my decision making. So that's why this question becoming important, like to understand fundamental attributability of this problem. So in the recently, like past 2 years, my student and I were actually like dive into those control problem and then compare with the literature. Like in the literature, some assumption people make, like the system will be homogeneous or invariant, but in application, those assumptions probably not going to hold. So we focus on the network control problem, the linear quadratic control problem, and we're actually able to show indeed, with the local controller can achieve good performance compared with the global optimal controller, and how the gap between the optimal local controller and the optimal global controller can decays exponentially with the like increase of the neighborhood size. And later I will show you one slide, and indeed like how you look at this exponential decaying, it's indeed actually decays gracefully if the system has the local interaction structure. Now, that's kind of first challenge, and we kind of feel, okay, now we actually can go ahead to find the local policy because local policy has a potential to achieve good performance. But now for the local policy, how are we going to really learn it? What I showed earlier is about single system. And you can see for the single system, given the large state action pair, it's already difficult. Now, for the multi-agent network case, what should we do? Now, for the active, we already say we can do the local policy parameterization, but what about for the critic? Like because everyone's still coupled, so once putting a policy, and then the global, everyone's queue was still kind of coupled with everyone. So how are we going to do it? I just have one slide to show you the high level ideas. Indeed, we will still, because it's impossible for individual agent to keep an eye on the global system. So we'll have the function to evaluate the local policy using those local state and action observation. Now, we still have like continuous state, continuous action. How are we going to generalize the representation I talked about earlier to this network case? Now, this is how we're going to generate. We're going to have this kind of things called a local feature representation. Now, our system dynamics, as I showed earlier, so we will have like the state Si prime will depend on the neighbor's state, his own action, and some randomness. So again, writing down as a state transition probability. So for this local state transition probability, do the decomposition. And that decomposition, the phi will depend on the neighbor's information. That's why the feature. Now, what's going to be the feature of the cost to go? It's going to be chrono product of those local features among myself and also my neighbors. So that's what how we're going to generalize the representation from the single system to the network system. We have a theoretical guarantee. Like when we did, you see we had a kind of two truncation. One the truncation about the global system to individual agent information based on local information. And there's another truncation, which is a feature truncation. So we're just going to use in those local feature chrono product to represent the feature. And again, what you can show is degrade gracefully, like as you increase the size of the neighborhood, we're getting better and better. Now, in summary, how are we going to read like developing a method for the network case? Just have a local actor, local critic, and then to again fit into those kind of IO framework, like any kind of method you prefer and do the interaction. Now, let me talk about the simulation result, which is actually quite inspiring, insightful for the figure. So first of all, the Kij, so we did the thermal control, which is the linear system. So we solved the optimal K, and the optimal K is can do the LQR problem. You get in the optimal K. So you look at this is the log curve. Indeed, the Kij means how much like the dependency from node I depending on node J. Indeed, you look at here, it degrades exponentially fast. So it means we do not need many hop of information. And then on the other side, which is the learning curve, which is a very interesting one. So you look at the optimal control. Optimal control, they have the 50, really the ring case. And so 50 means having everyone's information, and that's the black dash line. So even with just using the 3 hop of neighbors information, the red dash line is already kind of achieved the similar performance of the optimal controller. And this is about to getting the control of the truncation. Now, the solid line is through our representation RL method. Indeed, it's actually learned the optimal local controller. And then another interesting part, look at the orange one. So orange one, the dash line, is like we got the optimal K through the LQR, and we do the truncation just by using like 1 hop of information. And that's the orange dash line. And that's just do the truncation of the optimal controller, not necessarily the optimal. So indeed, like for our IO method, we actually learned a better local controller. So that is a solid orange line. Now, since the method is a general IO method, we can actually easily extend to the nonlinear system. So we did this parameter synchronization problem, trying to synchronize the frequency of individual node. And we compare with the IO method without using the representation. So because the system, like putting here n equal 40, it's kind of like relatively large scale. So without any kind of representation, it's becoming a challenge for the IO method to learn. Like kind of, you look at here, you actually will jump, go in there, we actually like rerun a long time. It's very hard to like predict what really the learning curve will be. The orange one is with our local representation. There is a learning curve, it's much more stable. And from the simulator, you can look at here, without representation, the always some node is not synchronized. And with the representation, like because we had a scalable representation, we'll do much better. So this is what's going on. The some node is always not going to synchronize with others. So with that, I almost conclude my talk. So I first talk about the just single plant, right? Where the representation come from, the model base, and we can see from the model base, you can see the method is not really like our representation IO method is not the model-free method. It's more like something between. It's a model-free and a model base, and if how much information you put, you can always keep your information in this kind of unknown F in the feature representation. And we show the application to the sim-to-real imitation learning. They're all useful. And the network case, like we do the local policy, local feature representation, and there are a lot of ongoing work. And like especially I was spending probably 2 minutes to talk about active representation because I haven't really talked about like everything about the Q representation. But when we doing the nonlinear control, you actually know everything. If I pick a bad representation for my policy, no matter how fancy method is, the performance it will be limited. Now for the actor, in order to put in a very general representation, a very natural way to do it is actually using the diffusion policy. Again, I want to kind of put in like the take-home message is like my original viewpoint is don't look at state space model, look at state transition probability. And for this one, similarly, don't just view your control policy as a determinist case control policy. Look at the control policy as the distribution, conditional distribution on the action, condition on the state. And that will also be in connection with the generative AI approach. Like here we do the diffusion policy to represent. I'm not going to have time to talk about how we're going to train the diffusion policy. On the high level, what diffusion policy is anytime when we actually do the getting the ultimate policy, we'll start as kind of some like Gaussian noise and just do the inference, do a few steps of denoising. And then this is a denoise pi can approximate any kind of the policy we want to do. So the better thing is we're building the connection of the energy-based model of the Q function we evaluated. So if you're interested, So this the paper, this is actually kind of my favorite paper last year, has the details, how we go ahead to train this policy. We actually use this diffusion policy on the pushing T task. And we did like this one, originally I saw going to do a few shots of sim to real. We actually didn't need to do any kind of like training once we bring from the simulation to the real system. There's actually 0 shot sim to real. We had different blocks, different goal locations, and different letters. And we also try to change the different friction to kind of mimic the different dynamics. And again, the control policy just works straightforward from our RL diffusion policy. So with that, I want to conclude my talk. I kind of touched those challenges: data, scalability, safety, sim to real, and then many other things I don't have time to touch. If you interesting, like all those work have been available in my Google Scholar, and including like the different application. And I will say the application on the engineering system and application on the biosystem and also the robotics are very different. Like where the terminology going to plug in is kind of have a different experience. So with that, I would like to conclude my talk and open up for questions. Thank you.
Thank you, Professor. It's a really interesting talk, and we really enjoy it. So now it's our Q&A session. Let me from my question maybe first. So I had a really small question, like when you talk about representation, like you say, when you have the new task or new environment, you're gonna collect the new data and you're gonna update your tool based on this new feature vector. I just wondering, like, because like for the transfer learning, for example, we also have some similar environment, similar task. This feature vector also have some capability for this transfer learning?
Yes. So we actually had a paper ongoing one. So we did the multitask transfer learning. Like for example, when you say the trajectory tracking one, like because objective different, but then dynamics actually shared. So we're actually able to using this one to show like we by doing this kind of representation based transfer learning will do better than like not going to really share like other type of transfer learning. Yes.
Okay, thank you, Professor. So let me transfer the questions from the comments from YouTube Live. The first one, could you please explain again the intuition behind how the features collected, in some way helping with robustness in the case of drone in the presence of the disturbance from the fan? Like, yeah, it's like disturbance from the fan. You collect kind of helping
Yeah,
you
so
to
like we didn't do like a very sophisticated way to let me go there. Like for example, this one, so we just go ahead. So we had a feature from simulator and we had our feature learned from the previous one without the fan. And then we turn the fan speed and then we got a new data and then we just using the new data to learn the new feature. So we actually the feature from simulator original, like a non-windy environment and then the windy environment. And then we train the policy. So that's it. And once we train the policy for the last one, the robustness test, we train the wind speed. We didn't do any further tuning anymore. It's just like the policy learned under this kind of, we turn on the fan speed and we kind of put in the strongest fan speed we had from this one. That's how we did for this experiment.
Okay. There's gonna be another question. Is Professor Lee, I wonder how the theory of spectral representation would be different if we had partial observation instead.
Great question. So I always like partial observer system is always difficult, especially for theoretical work. And theoretical work, I think in the past few years, people, even in the IL community, when people work on the partial observer system, they're making some assumptions, right? Even it's partial observed, but then my partial observation probably able to recover enough information of the state. That's I think is kind of doable. But then without that, you can making some assumption about like how many hop of those history able to recover the state information. For those, like theoretically, people can do something. And the representation similarly. So my collaborator Bo actually has a paper on the POEMDB, which is like putting like the multi history and putting the decomposition framework. So empirically has some performance. In our survey paper, we actually mentioned that as well. So, but summarize, I want to say it's still open question. And this is about from the IL side. And then I was working on a lot on the LQG side. So because for LQG, we actually know what's really open controller, trying to understand the optimization landscape. It's also difficult. So because the connectivity and like, like for the optimal controller is not unique, right? You can do the similarity transformation. So that's a cost problem for the post optimization, like where it's heading to. So again, like summary is still like ongoing open question, but then empirically people can try those methods and under assumptions, people have some result. But like for the general one, it's still just people go out to try putting a history of the information and then to guide the action design.
Okay, due to the time limit, let's conclude maybe with one more last question. But I'm gonna send some questions to the professors if they are still really want to answer. The last question can be, so for the data-driven representation learning, when the model is unknown, what function classes are typically used for phi and mu? Are these choices environment dependent or can be generally?
Great question. So I also like one quick answer to that question will be our paper, this one. You can check the code. So there's still a lot of engineering things we can play with it. Like if our model base, right, we know we just follow this kind of theorem doing the kind of Fourier series as a feature space. But when we don't have the model, right, since we don't have a model, like why just constrain ourselves on that one? But you can actually do that one. That's why I should kind of imply your last layer is going to be sine cosine, the Fourier layer. And the earlier one, like the VSA, you can still open up to any kind of representation you're going to pick. The empirically, so the one thing I want is from the method theorem is this. When we try to learn, we actually can do general nonlinear representation for the feature space. That's actually what we actually did for most of the empirical data-driven method. And for that part, what we one very useful tip is from what I was presenting is a state dynamics feature and the Q feature, they should share the same feature. So if you actually putting down share the feature, like here, the VSA from the P, and then putting this similar phi to this Q, this one, look at this figure here. As long as we do that, it will have a good performance. And you actually can try different kind of VSA representation. But like one take-home message, like they should share like a common head. Hope that's kind of answer this kind of empirical question. But you can also dive into the code to see for different application how we did for this kind of different data-driven method.
Okay, thank you, Professor. I think we're gonna conclude here. But thank you so much. I mean,
Thank you
it's
so
really
much.
interesting and insightful talk, and hope you have a great day.
Thank you so much. Feel free to email me questions.
Okay, thank you. Bye bye.
Bye.